Now I am going to discuss the sequence networks of power system components. So here we have to discuss about the transmission line, the transformer and the generator, which is nothing but the alternator. Now first coming to the sequence network of three-phase transmission line. So I have considered three-phase transmission line with three phases and a neutral wire. Now A dash, B dash, C dash and N dash are the transmission line network which I have considered. Now coming to the impedances, ZAA is the impedance of the transmission line AA dash, similarly ZBB and ZCC and ZNN. And we also have the mutual impedances, that is the second phase influences the first phase and whose impedance is represented by ZAB. Similarly, we have ZCA and ZBA. So ZAB, ZBC and ZCA are the mutual impedances. Similarly, these impedances are also going to affect the neutral impedance. We have those impedances as ZAN, ZBN and ZCN. And coming to the voltages on one side of the transmission line, here I have considered VAN is the voltage between transmission line phase A and neutral wire, and VBN is the voltage between phase B and neutral. Similarly, VCN is the voltage between phase C and neutral wire. So similarly, on the other side of the transmission line, we are going to represent those voltages as VA dash N dash, VB dash N dash and VC dash N dash. And also the currents flowing in the transmission lines are represented by IA, IB, IC and the neutral current IN. So that was what represented here. VAN, VBN, VCN are the voltages on one side, and VA dash N dash, VB dash N dash, VC dash N dash are the voltages on the other side, and the currents IA, IB, IC and IN are the currents flowing through A, B, C and neutral wire respectively. So as I've said, due to the mutual impedance also the phases are being affected. So that's why we are going to consider ZAB, ZBC and ZCA, and also the impedances ZAN, ZBN and ZCN. So assume that the transmission line is fully transposed to make it symmetrical. So why we transpose the transmission line? To make it symmetrical, we are going to transpose the transmission line. So since we are making it symmetrical, all the impedances becomes equal. So instead of representing ZAA, ZBB, ZCC, since they are symmetrical, I am going to write them as ZAA is equal to ZBB equal to ZCC and ZAB equal to ZBC equal to ZCA, and similarly ZAN equal to ZBN equal to ZCN. Now I am going to just consider phase A and neutral wire. So if I look at the network here, ZAA is the impedance of that particular phase A dash, and coming to the drop here, it is ZAB IB, which is due to the impedance ZAB, and the current flowing in BB dash is IB. So yes, and coming to the impedance here, it is due to the phase C, which is denoted by ZCA into IC, and this drop is due to the neutral wire. But we have considered that the sequence impedances, the impedances are same because they are symmetrical. So instead of ZCA, I am going to represent it as ZAB only, and here it is ZAN. And coming to the neutral wire, ZNN is the impedance of the neutral wire, and ZAN IA is the drop due to phase A. ZBN IB, this is due to drop in phase B, and this is due to drop due to in phase C. So since ZAN equal to ZBN equal to ZCN, here I have represented all in terms of A: ZAN IA, ZAN IB and ZAN IC. So writing all the terms in terms of A. Now applying KVL in this particular network, what I obtain is the voltage across this VAN can be written as the drop here ZAA into IA plus ZAB IB plus ZAB IC plus ZAN IN plus VA dash N dash minus, if you observe this notation, this all will be in the opposite direction. So I have taken minus sign here, and all the drops will be having negative sign. So the drop here is Zn and In. Here it is minus Zan Ic minus Zan Ib minus Zan Ia. So for all I have considered negative sign before itself. Now taking this term Va dash N dash to the left hand side, I can represent this as Van minus Va dash N dash. Now taking the terms Ia, Ib, Ic common. So Zaa minus Zan. Where is the Ia term here? So the coefficient is Zan and we have a negative sign here. So Zaa minus Zan times Ia plus now Zab minus Zan into Ib plus Zab minus Zan times Ic plus Zan minus Znn times In. Now if you observe, these two terms are same. So when I take this as common, I can write it as Zab minus Zan into Ib plus Ic. The other terms will be same. Now if you observe from the circuit, the sum of currents, that is Ia plus Ib plus Ic plus In equal to 0. So from this I can write In as minus of Ia plus Ib plus Ic. Now you substitute this equation in equation 1. So when you substitute that, in place of In you will be writing minus of Ia plus Ib plus Ic. That is what is written here. Now again taking all the currents common. So if you observe, we have Za minus Zan initially. Now after substituting this In value, here I am going to have this term. So if you observe, minus Ia into Zan plus Znn into Ia. So that was what written here. Zaa minus Zan, that is already there, and Zan into minus Ia. So minus Zan, minus into minus will become plus. So it is plus Znn into Ia. Similarly, the terms of Ib and Ic can be written like this. So we have 2 times Zan term in each of the terms. So it becomes, the first term becomes Zaa plus Znn minus 2 Zan. The second term is Zab plus Zan minus 2 Zan. Similarly, the third term Zab plus Znn minus 2 Zan. So after simplifying those terms, I get this equation 4. So which is the voltage difference between Va and Va dash N dash. So similarly, if you write for the phase B and phase C, I am going to get Vbn minus Vb dash N dash is equal to. See, if you observe, and I have written Van minus Va dash N dash, I have obtained here Zaa plus Znn minus 2 Zan. Now this term is going to appear for the second term for the current Ib. Because this we are writing for B phase, that particular term is going to come here. These are the similar terms, that's why I have taken them directly. If you want to derive it, take the same as A dash and neutral wire. Here you consider B dash and N dash neutral wire and write the equations, and then when you simplify this, you are going to get this equation. Similarly, when you write for C, phase C, that is Vcn minus Vc dash N dash, you are going to get this particular term for the third case. So if you observe Zaa, it is nothing but it is representing self impedance term. So what I am going to do is I am going to call this particular term as self impedance. So which is represented by Zs, and it is nothing but Zaa plus Znn minus 2 Zan. And the other terms, which are Zab plus Znn minus 2 Zan, it is represented as mutual impedance and represented by Zm. So now I am going to represent these three equations 4, 5 and 6 in the matrix form. So Va dash. So instead of writing VAN minus VA dash N dash, I can write this as VAA dash, which is VAN minus VA dash N dash. And since I have considered this as the self impedance and denoted by ZS, this total term is written as ZS in the matrix. The remaining two terms, this and this, are the mutual impedances. So that's why they are represented with Zm. Similarly, if it consider the fifth equation, the self impedance term got here for the second term, so that's why it is represented here. The remaining two are the mutual impedances. Similarly, in the last equation, the self impedance term is in the third term, so Zs is represented here. So Zs, Zm, 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 Zs, Zm, 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 Zs into Ia, Ib, Ic. This is matrix is called Z, which is impedance matrix of all the phases, which is symmetry. But these are all the phase, in terms of phases we are talking about. But if you want them in the symmetrical component terms, that is symmetrical component impedance, I have to write that matrix. To obtain that symmetrical component impedance matrix, Z symmetrical is equal to A inverse ZA. This A matrix is already discussed earlier, which is given by A inverse is given by 1 by 3 times 1 1 1 1 A square 1 A square, and A matrix is 1 1 1 1 A square A 1 A square. And we also know that A is nothing but 1 at an angle 120 degrees. So after simplifying this or substituting these two matrices in the above equation, I am going to get the symmetrical component matrix impedance matrix as Z0 0 0 0 Z1 0 0 0 Z2, where Z0 is nothing but Zs plus 2Zm and Z1 is equal to Z2, whose value is Zs minus Zm. This you can just simplify by substituting those matrices and get. Now the voltage drop of 0 sequence, positive sequence and negative sequence is given by V0 minus V0 dash is Z0 into I0, where Z0 is the impedance of that 0 sequence network. Similarly, V1 minus V1 dash, which is Z1 I1, V2 minus V2 dash is equal to Z2 I2. The above three equations are independent to each other, that is, they are not dependent on any other equation. So these three equations can be represented by three individual networks. So 0 sequence network can be represented as, see if you observe, it is V0 V0 dash. So the voltage difference V0 minus V0 dash is nothing but the drop across this impedance, which is Z0, and if the current flowing is I0 here, and this Z0 is given by Zs plus 2Zm. But we know that actual Zs and Zm values, so when you substitute that, you are going to get Z0 as Zaa plus 2Zab. Similarly, the positive sequence network V1 V1 dash, the potential difference across this V1 minus V1 dash is the drop across this, which is Z1 into, and the current I1 is the current flowing through this network. And if you simplify this for Z1, we are going to get Zaa minus Zab. Similarly, the negative sequence network V2 minus V2 dash is equal to drop across this Z2 into I2. So when you simplify this, you are going to get Z2 as Zaa minus Zab. And we also observe that Z1 equal to Z2. So here what you have to observe is the positive and negative sequence impedance are equal in a transmission line, that is Z1 equal to Z2. And the 0 sequence impedance is much larger than positive sequence and negative sequence impedance. It means, so the relation is Z1 equal to Z2 is less than Z0. That means Z0 is very much high compared to Z1 and Z2. The typical values could be Z0 is 2 to 3.5 times of Z1. So this is about the sequence network of a three-phase transmission line.